There is a picture your browser paints with your graphics chip that you never actually see. No window opens, nothing is drawn on the page, and yet in the moment it takes a site to load, a script can learn something quietly identifying about the exact hardware inside your machine. It is called WebGL Fingerprinting, and it is one of the heaviest signals in this whole space because it reaches past the browser and reads the GPU itself. Today I want to explain defensively and in plain terms what WebGL fingerprinting is, how detection reads it, and why so many tools that spoof the obvious things still leak this one. Quick note on framing before I start. I run real proxy and cloud phone farms, and I test how these browsers handle fingerprinting for a living. So the hardware signals like this one are the layer I spent the most time on. I am going to keep this third person and defensive the whole way, how the technique works and how it is defended against, not a recipe for beating any particular site. And there are no undetectable promises anywhere. Understanding this signal removes one more contradiction from a setup. It does not make anything invisible. Start with what WebGL actually is, because the name hides it. WebGL is the browser feature that lets a page render graphics using your GPU, the same graphics chip that draws your games and your video. A fingerprinting script does not need to show you anything to use it. The first thing it reaches for is a pair of text strings the driver exposes, the vendor and the renderer. And on most machines, those strings spell out your exact graphics card and a hint of the driver behind it. That alone is a remarkably specific label for a piece of hardware. The second leak is the deeper one, and it works exactly like the canvas. The script asks WebGL to render a small three-dimensional scene, a shape with some lighting and texture entirely off-screen, then reads the resulting pixels straight back out and hashes them into a short string. The numbers that come back depend on your GPU, its driver, and the operating system underneath, and two machines that are even slightly different produce pixels that differ in the tiniest places. Nothing appears on screen. The scene is drawn, measured, and thrown away in a fraction of a second. There is a third layer on top of those two. WebGL exposes a long list of technical parameters about what your hardware can do, the largest texture it can handle, the precision of its math, the exact set of extensions it supports. Each of those values is characteristic of a particular GPU and driver combination, and together they add up to a rich, detailed portrait. So WebGL leaks three ways at once: as a name, as a rendered image, and as a specification sheet. And a detector can read all three in the same breath. Here is why that combination is worth so much to a tracker. The GPU model and driver are already narrow, far narrower than something like your screen size, and the rendered output is stable and characteristic of your specific machine. Plot the vendor string, the pixel hash, and the parameter list together, and you have one of the highest entropy signals a browser hands out. A description detailed enough to pick your device out of a very large crowd. That is exactly the kind of signal detection is built around. And the property everything hinges on is the same one that governs the canvas and the audio signal. A real device returns the same WebGL values every single time, reload after reload, day after day. Your graphics card does not change between page loads. Your driver does not quietly rewrite itself, so a genuine machine produces a WebGL fingerprint that sits perfectly still. Hold on to that, because stability is normal, and it is precisely the property a careless spoofing strategy breaks. Anti-detect tools respond to WebGL in a few familiar ways. Some rewrite the vendor and renderer strings so the page reads a different graphics card than the real one. Some inject a small amount of noise into the rendered pixels so the hash never matches the true hardware. Some spoof the parameter list to match a claimed card, and a few try to disable WebGL outright. Each approach trades hiding the real GPU against still looking like an ordinary machine, and the gap between those two goals is where most tools quietly fail. The first place they fail is agreement, because WebGL does not stand alone. The canvas and WebGL are both drawn by the same GPU, so their stories have to match, and both have to agree with the operating system the profile claims to be. A profile that reports a Windows machine at the page level, while its web renderer names an Apple graphics chip, is a contradiction a detector reads instantly. Changing the string is easy, Keeping the string, the pixels, the canvas, and the platform all pointing at one believable machine is the hard part, and it is the part that actually matters. Then there is the per-read problem, the same trap that catches the canvas and the audio signal. If a tool perturbs the rendered pixels on every single read, the hash comes out different each time, and no real GPU behaves that way. A genuine machine draws the identical scene the identical way every time you ask. So a WebGL hash that shifts between two reads on the same page is not hidden, it is waving a flag because it is announcing that something is actively tampering with the output. Instability is not protection here, it is a tell. Picking the replacement is harder than it sounds too. The spoofed renderer string has to name a real, plausible graphics card that actually exists and is common enough to blend in, not some invented label, and not a card that would be strange on the kind of machine the profile claims to be. Worse, a lot of naive setups fall back to a software renderer, the generic fallback a browser uses when there is no real GPU available, and that value is itself rare and obvious. A machine reporting software rendering, where a normal user would report real hardware, has simply traded one anomaly for another, and the string is not enough on its own because the parameters have to back it up. If the renderer claims a particular graphics card, but the reported texture limits, the precision values, and the extension list do not match what that card really supports, the profile is telling two stories about the same hardware. Detectors know what real cards report, so a vendor string bolted onto the wrong specification sheet is a contradiction sitting in plain view. A good spoof has to make the whole hardware description internally consistent, not just swap the headline name. There is a mistake that quietly undoes the whole point, and it mirrors the noise problem from the other side. If a tool hands every one of your profiles the identical spoofed GPU, then all of those profiles now share one WebGL fingerprint. You built separate profiles precisely so they would not link together, and a shared graphics signature relinks them anyway, no matter how different their cookies or their proxies are. A good implementation gives each profile its own distinct but plausible and stable GPU story, so your profiles match neither the real hardware nor each other. Mobile complicates this the way it complicates everything. Phones use entirely different graphics chips than desktops, the ones built into phone processors rather than into a gaming machine, and they report different renderer strings and different capabilities. A profile that claims to be a phone while its WebGL describes a desktop graphics card is the same contradiction wearing mobile clothing. Believable mobile emulation has to reach all the way down to the GPU the profile pretends to have, which is one more reason genuine mobile profiles are far harder to produce than swapping a handful of reported values. On the detector side, the checks are exactly what you would expect by now. A fingerprinting script reads the vendor and renderer strings, renders its own scene, and hashes the pixels, pulls the full parameter and extension list, and then cross-references all of it against the canvas, the reported platform, and the rest of the hardware picture. It reads the values more than once to see if they hold still. The well-known open-source consistency tests do precisely this, and they will happily report a WebGL layer that disagrees with itself or with the machine around it. There is a subtler trap in the middle of all this. If your WebGL fingerprint is common, it blends in but tells a tracker less. If it is rare, it identifies you strongly. A spoof that invents an exotic or impossible graphics card hands you a fingerprint that is both unusual and, often, internally inconsistent, the worst of both worlds. The target is not the most unique GPU you can fake, it is a plausible, common graphics card that a lot of ordinary people genuinely have, reported consistently every single time. More exotic is not safer here, it is usually the opposite. And like every signal in this space, this one drifts. A graphics driver update changes how your GPU renders that off-screen scene, a browser update shifts how WebGL behaves, an operating system upgrade moves the ground underneath, and a detector updates its checks to catch the current generation of spoofs. A WebGL setup that tested clean 3 months ago can start leaking or contradicting itself without you touching a thing. And because none of it is visible from your side, it is easy to keep trusting a profile long after it went stale. Recheck it, especially right after any driver, browser, or tool update lands. The practical audit is short and worth running before you trust a profile. Load a public WebGL fingerprint test twice and confirm the values are identical both times, not shifting between reads. Confirm the renderer string names a real plausible graphics card and not a software fallback, and that it matches the operating system the profile claims. Confirm the WebGL story agrees with the canvas result since both come from the same GPU. And confirm two of your own profiles come out with genuinely different GPU stories. Stable, plausible, consistent, and distinct? Those are the same questions a real detector is asking. So be clear about what getting this right does and does not buy you. A coherent WebGL fingerprint removes one of the heaviest and most detailed contradictions a browser can leak, and it closes a gap that plenty of tools handle carelessly. It does nothing about your behavior, your account history, or how detection shifts over the months you use an account, and it does not make anything undetectable. It is one more layer made consistent, one more contradiction removed from the pile, which is real and worth doing, but it is a piece of the picture, not the whole of it. Which browsers actually keep the WebGL consistent under testing? The string, the pixels, and the parameters all agreeing, and which ones leak the real GPU, or fake and impossible one? Is written up hands-on with no undetectable promises anywhere in the full written reviews and tested pics at antidetectbrowser.org. If this cleared up a signal you had never thought to check, subscribe for more on the hardware layers underneath the ones everybody talks about. And I will see you in the next one.